1 minute ago, Mount Etna just erupted, and what it spewed out has never been seen before. If you think you understand volcanoes, this discovery will completely shatter everything scientists thought they knew about what's hiding deep inside our planet right now. While you're watching this video, Mount Etna is releasing a mysterious glowing material that doesn't match anything in geological records. We're not talking about typical lava or familiar volcanic rock. We're talking about something that appears to have formed deeper inside Earth than any volcano has ever accessed before. The eruption escalated into a violent pyroclastic flow, racing at 140 kilometers per hour, scorching land that was already barren, suggesting this isn't behaving like any normal volcanic event. Scientists are calling it a paroxysm, a rare explosive outburst that signals Etna may be entering completely uncharted territory. But when researchers rushed the mysterious material to labs for analysis, what they found made their blood run cold. It wasn't basalt, it wasn't andesite, it wasn't any mineral they'd ever seen before. The composition suggests Etna is now tapping into mantle and crustal material from depths that should be impossible to reach. Here's what's keeping volcanologists awake at night. Etna's internal structure is showing signs of instability that mirror conditions from 7,200 years ago, right before a massive flank collapse triggered a Mediterranean tsunami that reshaped entire coastlines. The question isn't just what this strange substance is. It's whether Mount Etna is trying to warn us about something catastrophic that's building deep beneath our feet. Rising more than 3,300 meters above the Sicilian plain, Mount Etna looms as both a landmark and a warning. Its summit, crowned with shifting craters, is visible for miles, a constant reminder that the ground here is never truly at rest. For centuries, Etna has shaped the fate of eastern Sicily, its slopes carved by rivers of fire, and its name woven into ancient myth. UNESCO designated it a World Heritage Site not just for its beauty, but for its restless spirit and the scientific record it holds in stone. Etna's history is written in layers of ash and lava, each marking a moment of upheaval. Roman chroniclers described nights lit by fountains of flame, while medieval villagers told stories of the mountain's anger swallowing fields and homes. Yet for all its drama, Etna's rhythms have become familiar. A cycle of rumbling unrest, brief eruptions, and long, uneasy calm. Mount Etna's restlessness is legendary, even among volcanoes. For more than 3,500 years, this mountain has rarely slept. Historic records and ancient chronicles agree. Eruptions are not the exception. They are the rule. On average, Etna erupts in some form more than 8 out of every 10 years. That's a higher frequency than almost any other major volcano on the planet. In the past century alone, over 60 eruptive episodes have been logged, some lasting mere hours, others stretching for months. But even those dramatic moments are just the latest in a long chain. Archaeologists have traced layers of ash and lava back through Roman times and even further to Bronze Age settlements buried beneath black rock. Each layer is a timestamp, marking yet another burst of energy from deep inside the Earth. Scientists at the Osservatorio Etneo monitor every tremor and plume, mapping the mountain's pulse with seismographs and satellite feeds. They have learned to read its moods, watching for subtle changes that can mean the difference between spectacle and disaster. The volcano's constant output means that new craters, cones, and lava fields appear with startling regularity. In some years, the summit changes shape multiple times, vents opening, closing, and shifting position as if the mountain itself is breathing. On February 8, 2025, that familiar pattern began to shift. A swarm of small earthquakes rippled beneath the summit, more frequent and deeper than usual. Instruments picked up a tremor, low and insistent, echoing through chambers far below the surface. The mountain's breathing changed, and with it, a sense of unease settled over the observatory. For those who know Etna best, the message was clear. Something beneath the volcano was stirring, and the old rules might no longer apply. Deep beneath Mount Etna, the story of every eruption begins in a hidden world of molten rock and shifting pressure. Scientists have spent decades piecing together a map of Etna's interior, using seismic waves and chemical signatures as their guide. At the base of this system lies a vast reservoir, nearly 11 kilometers below the surface, a depth where temperatures and pressures are high enough to keep rock in a perpetual state of melt. This isn't a simple single chamber. Instead, Etna's plumbing stretches upward in tiers, with magma pausing at several levels before making its final push to the summit. Each reservoir acts like a staging area, where new magma mixes with older batches and picks up clues about its journey. The lava that typically reaches the surface carries a familiar fingerprint. Petrologists describe a mineral trio, olivine, clinopyroxene, and plagioclase, as the backbone of Etna's rocks. These minerals crystallize out as magma cools and rises, locking in information about temperature, pressure, and even the source of the melt. Most eruptions produce basaltic lava, rich in iron and magnesium, with a composition that matches what's expected from a mantle-derived source modified by its passage through the crust. Over the last 50 years, careful analysis has shown a steady trend, a gradual enrichment in potassium and strontium, likely from the assimilation of sedimentary rocks as magma rises through the upper 10 to 15 kilometers of crust. But even with these shifts, the basic signature remains consistent. Etna's lavas are well documented, their mineralogy charted in detail across thousands of samples and decades of research. This baseline matters. It gives scientists a benchmark for comparison, a way to spot anything out of the ordinary. And on February 13th, that baseline was about to be shattered. At dawn on February 13th, a team of volcanologists and a helicopter crew prepared for a mission that defied common sense. The summit flanks were already trembling from frequent quakes, but the call came through. A new flow had broken loose, stretching 3 kilometers down the south slope, brighter and denser than anything seen in recent memory. Sensors warned of ash columns rising fast, and aviation alerts snapped to red. Still, the team pressed upward, racing against the mounting instability. The air near the crater was thick with sulfur and heat. Every few minutes, the ground lurched beneath their boots, sending loose rocks skittering toward the valley below. The lead volcanologist signaled for the others to hold back as he edged closer to the source, a glowing, viscous stream pulsing from a fresh vent. With protective gloves and tongs, he scooped a sample into a reinforced canister, the material radiating heat through the metal like a live ember. Ash blasts rattled the ridge, and the radio crackled with warnings of a possible collapse. Suddenly, a deep tremor sent a wave of debris tumbling downslope. The team scrambled, clutching their prize. Above them, the helicopter hovered, rotors slicing through the haze. The extraction was frantic. One by one, they were hauled aboard as the wind shifted and a curtain of ash swept over the landing zone. Within minutes, the mountain swallowed their footprints. The sample, still warm, was rushed down the mountain and handed off to a secure lab team, beginning a chain of custody that would soon draw the attention of scientists around the world. Inside the Catania laboratory, the sample arrived still radiating heat through its double-sealed container. Chain of custody protocol demanded immediate transfer to the isolation chamber, but urgency outpaced caution. A technician in heat-resistant gloves logged the time, 8:12 a.m., and reached for the reinforced latch. The instant the seal broke, a sharp hiss filled the room, followed by a burst of vapor that shimmered with an unnatural glow. Sensors flashed red. Alarms blared. The containment officer shouted for evacuation as a caustic sting swept through the air. In the confusion, a gloved hand brushed the edge of the vessel. The technician recoiled, clutching a wrist now ringed with a raw, angry welt, evidence of a burn from contact with the unknown substance. Automated shutters slammed down, locking the sample inside negative pressure containment. Emergency protocols triggered a full lab lockdown. Within minutes, the corridor filled with the thud of boots and the clipped voices of hazard response staff. Medical responders hustled the injured technician away, his burns minor, but his shock unmistakable. Outside the sealed doors, senior scientists watched monitors as real-time data flickered across the screens. The material's surface temperature refused to drop, and its vapor cloud defied standard filtration. Every routine analysis failed, leaving only questions. In less than 15 minutes, a routine handoff had spiraled into a crisis. The sample, once a scientific prize, now sat at the center of a biohazard scare. For the team, the message was clear. Whatever had come out of Etna was not just unfamiliar, it was unpredictable, and it would not give up its secrets easily. The sample arrived at the INGV laboratory in Catania under double lock, its chain of custody tag signed by 3 hands. Within hours, the first results sent a ripple through the network of European partner labs. X-ray diffraction, the gold standard for mineral identification, returned a pattern that matched nothing in the International Center for Diffraction data. Peaks appeared where no known silicate, oxide, or glass should register. The analyst, Dr. Sofia Bernardi, reviewed the calibration, then ran the scan again. Same result. Unmatched signatures, a fingerprint from nowhere. She flagged the anomaly and uploaded the raw data to the central server, triggering an urgent peer alert. In Berlin, the geochemistry team at GFZ received their split of the sample. Inductively coupled plasma mass spectrometry, designed to detect parts per billion, pinged on trace elements at levels far above the norm. Yttrium, cerium, and a spike in lanthanides, usually reserved for deep mantle xenoliths. The lead chemist, Dr. Felix Kruger, checked for contamination, then for instrument drift. When the numbers held, he called for a halt and a blind retest. Meanwhile, the Paris lab reported a third contradiction. Raman spectroscopy found ambiguous lattice structures, some reminiscent of high-pressure phases, others simply noise. The French team questioned whether the sample had been altered in transit or if it was a composite, a mixture of volcanic glass and something else. Emails flew between labs, each thread more urgent than the last. Was this a new mineral, a reaction product from extreme heat and pressure, or a fluke? The Catania lab pointed to the XRD, no match in the terrestrial database. Berlin countered with their trace element chart, levels incompatible with surface magmas. Paris pressed for a peer review before any public statement. The debate spilled into late-night video calls, with analysts scrutinizing spectra pixel by pixel, arguing over baselines and background subtraction. Some invoked contamination, others a flaw in the chain of custody, but none could square the data with ordinary volcanic science. By the end of the week, the sample had become a scientific riddle. remote sensing specialists gathered in makeshift command tents, their screens lit with the latest data from fiber optic cables and seismic arrays. The usual patterns of magma movement were gone. Now the instruments mapped out a patchwork of silent zones, places where expected signals simply vanished. These so-called muon gaps, detected by cosmic ray tomography, hinted at unexplained voids deep beneath the southeast crater. Theories flew across encrypted channels, hidden magma pockets, collapsed conduits, or something else entirely. Every fresh scan added urgency to the debate, and calls for a denser seismic array multiplied overnight. But the scientific mystery was only part of the story. Outside the scientific bubble, the world was watching and reacting. News leaked that two mining conglomerates had dispatched drones to Etna's slopes, searching for traces of rare elements in the aftermath of the eruption. The drone's presence triggered a storm of outrage. Environmental groups demanded answers, accusing corporations of exploiting a disaster for profit. In Catania, activist collectives organized marches, their banners reading, "Hands off Etna, no to mining in the shadow of the volcano." The demonstration drew hundreds, their chants echoing through the old city streets as officials scrambled to reassure the public that no mining permits would be granted. Within days, the debate spilled over into Parliament. Lawmakers called for an immediate ban on all non-scientific drone flights, while volcanologists pressed for expanded access to deploy new sensor arrays around the crater. The stakes had shifted. Etna was no longer just a scientific puzzle, but a battleground where technology, economics, and public trust collided. Here's what makes this even more frightening. Satellite data that should have been routine revealed something that sent chills through the research community. Confidential synthetic aperture radar interferograms showed asymmetric inflation concentrated along the southeast sector, exceeding the threshold set after the 2002 collapse scare. Civil defense analysts reviewing the raw displacement maps found peak values that doubled the warning line, signals that by protocol should have triggered a full-scale evacuation order. Infrasound records registered a low-frequency surge, a kind of acoustic warning that usually precedes major structural failure. High-resolution thermal imaging revealed a persistent hot zone, not just at the vent, but tracing a line beneath the southeast flank. The risk of sector collapse, an event capable of sending millions of tons of rock toward the sea, was now more than theoretical. This is where history becomes terrifying. 7,200 years ago, Etna experienced a massive flank collapse that triggered a tsunami across the Mediterranean. The structure of the volcano right now mirrors the conditions that existed just before that catastrophic event. Scientists are racing to determine if we're witnessing the early warning signs of a similar disaster. Mount Etna has erupted more than 200 times in recorded history, but the 2025 event stands alone. For the first time, scientists recovered a glowing substance that does not match any known volcanic mineral. Lab reports confirm it is neither basalt nor andesite, the standard products of Etna's eruptions. Seismic imaging and muon tomography reveal shifting voids deep below the summit, echoing the instability that led to the catastrophic flank collapse and tsunami 7,200 years ago. Yet as of today, no peer-reviewed publication has fully classified the new material, and no official risk assessment has determined the likelihood of a similar collapse. What is clear? Etna's behavior is changing in ways never documented before, drawing urgent attention from researchers and emergency planners across Europe. The mountain's secrets are now everyone's concern, and the demand for answers has never been louder. Until more data is released, the true origin and risk of the mysterious substance remain unresolved. A stark reminder that even our oldest, most studied volcanoes still hold secrets scientists are only beginning to uncover. The question that keeps experts awake at night isn't just what this substance is or where it came from. It's what it means for the future. Is Etna tapping into deeper sources of magma than ever before? Are we witnessing the beginning of a new eruptive phase that could last decades? And most terrifying of all, is the mountain showing us the warning signs of an impending collapse that could reshape the Mediterranean once again? For now, the monitoring continues. Every tremor is logged, every gas emission measured, every satellite pass analyzed for the slightest hint of what might come next. The people living in Etna's shadow know the mountain better than anyone, but even they admit that something has changed. The old rhythms, the familiar patterns no longer seem to apply. What came out of Mount Etna isn't just frightening because it's unknown. It's frightening because it suggests that everything we thought we understood about this volcano might be wrong. And if we're wrong about Etna, what else don't we know about the restless giants that shape our world?